So in this lesson I'm going to look at another example using the principle of conservation of linear momentum. Actually also in this example we'll be using it together with the principle of conservation of energy. So bodies which have a common velocity after impact are said to coalesce. We're going to be talking about coalescing objects here. So we've got a bullet of mass 0.15 kilos fired horizontally with a speed of 240 meters per second into a stationary block of mass 8. The block is suspended from a light rod of length 5. So I've got, some kind of bullet here, down here, and that bullet, gets projected, it gets shot out, and it goes and hits the rod and gets embedded in the rod. And together then, and the bullet and the rod swing up. They'll rotate around to some point and they'll stop eventually, and then they'll come back down. We want to find the angle theta that the rod will make with the vertical when the block comes to rest for the first time. Okay, so what I'm going to do is I'm going to be using two things here. I'm going to be using the principle of conservation of energy. If I know the total energy of this at the start, well, that's going to be equal to the total energy at the end. But what gives this energy, what gives this mass energy, is the bullet flying into it and hitting it, and that gives it some kind of kinetic energy. Note, with the rod, initially all of its energy, once the bullet hits it, it's hanging there, there's no energy, I suppose, and then the bullet hits it, it'll start to move and rotate. Initially all its energy will be kinetic, and at the end, when it gets to its final position, all its energy there will be potential. Okay? But my first job was to find at what speed the block moves away. So I'm going to use the principle of conservation of linear momentum. And again, write it out first. Here it is. It says that m1u1 plus m2u2 is equal to m1v1 plus m2v2. So m1u1, well, let's this be the bullet, the first object. Its mass is 0.15. Just double check that's given in kilograms. So it's 0.15 is the mass times its initial velocity. It has a big initial velocity of 240 plus the mass of the second object, which we know is 8, but its initial velocity is 0. It's not moving at all. It's stationary. So its initial velocity is 0. And that's going to equal to the mass of the bullet, 0.15, times the velocity of the bullet after impact, we don't know what that is, plus the mass of the block here, which would be 8, times, and again, the velocity of the block, we don't know, but the bullet becomes embedded, which means the block and the bullet together move off with a common velocity. They have coalesced. So the block becomes embedded, so afterwards the block and the bullet are going to move with the same speed or the same velocity. I'm going to call that v. Okay, bit of calculator work, tidying things up. Notice on the right hand side, that's just going to be 8.15 times whatever v is. And over on the left hand side, we're going to have 0.15 times 240, which is 36. 8 times 0 is just 0. So the velocity of the block and the bullet after impact is going to be 36 divided by 8.15, which I'm getting to be 720 over 163. 720 over 163. So that's going to be the velocity they move off with together. Okay, so it's going to be the velocity here at this position. We want to find this angle here that this makes. So I can find the height that this raises, so I can figure out this height. I know the rod has a length of 5, that's given. which means the whole, distance from there to there is 5. So if I can find out this height, I should be able to work out that distance, and from that I should be able to work out a value for theta. Okay, so I'm going to use the principle of conservation of energy. And the principle of conservation of energy says the total energy in position 1 will equal to the total energy in position 2. Again, we've looked at that in previous lessons. In position 1, all of its energy will be kinetic. In position 2, up here, when it has stopped, when it comes to rest, all of its energy is going to be potential. We're trying to find, the height where it comes to rest. Where does it come to rest? What's its height? What's its height? What's the height of the object? So there's the height in there. That's the height at which it comes to rest. So kinetic energy in position 1, well, kinetic energy is a half times m times v squared is equal to potential energy in position 2. Well, that's m times g times h. And notice, as always, when we use the principle of conservation of energy on an object, the masses cancel. So I'm going to get a half times, well, the velocity squared, that's 720 over 163 all squared. That's its velocity. We figured out that was its initial velocity. And that's going to equal to g multiplied by h. So to find h, the height to which it rises, we're just going to divide on both sides by g. So it's going to be 1 over 2g times 720 over 163 all squared. Okay, and those are awkward numbers. Whoever came up with this question, wasn't thinking about making this look very nice. So I'm going to use my calculator here. It's 1 over 2g. I'm going to let g be 9.8. And I'm going to multiply that by 720 over 163 squared. I'll just hit equals. Now what it's telling me here is the height, and I'm going to round that off and go to 4 decimals, 0.9955. So it goes up to 0.9955. Okay, so if we think about this, I can take a little right triangle out here, where this is the radius length of the circle, that's going to be 5. If that height is 0.9955, then this side here is just going to be the difference between that and 5. Remember, we said the whole length was 5, so we're going to subtract that from 5. And what we get is 4.004. Okay? And then we're going to find the angle. Well, remember your cosine formula. Cosine is adjacent over hypotenuse. So cosine inverse of adjacent 4.004 over the hypotenuse 5. That's going to give me my angle. Okay, so cosine inverse. And I'm getting about 36 point, and go to 2 decimal places, 78 degrees. Okay, so quite a bit in that as well. We had to use the principle of conservation of linear momentum. We had to use the principle of conservation of energy. And we had to, be able to use our trigonometric ratios and be able to, once we figured out height, be able to work out, solve this triangle. Okay, so that's the principle of conservation of linear momentum, and we'll be moving on to the next section in the next class. So section 6C, you should be able to attempt pretty much all the ordinary level questions at this stage.